Hi, I'm Miss Barber. This lesson is titled Functions. The learning objectives for this lesson are 1. Demonstrate understanding of the formal mathematical definition of the function. 2. Be able to evaluate a function, both numerically and also with variables and algebraic expressions. 3. Be able to determine the domain and range of functions. And 4. Be able to represent a function in a variety of ways. Let's get started. We'll start with I, definition of function. A function f is a rule that assigns to each element x in a set A, which we call the domain, exactly one element called f of x in a set B, which we call the range. That's the definition of a function. The symbol f parentheses x parentheses is read f of x or f at x and is called the value of f at x or the image of x under f. The set A is called the domain of the function, and the range of f is the set of all possible values of f of x as x varies throughout the domain. The symbol that represents an arbitrary number in the domain of f is an independent variable. The symbol that represents a number in the range of f is called a dependent variable. If we write y equals f of x, then x is the independent variable and y or f of x is the dependent variable. 2. Evaluate a function. To evaluate a function f at a number, substitute the number for the variable in f. 3. Domain of a function. The domain of a function is the set of all inputs for the function. If the function is given by an algebraic expression and the domain is not explicitly stated, then by convention, the domain of a function is the domain of the algebraic expression. That is, the set of all real numbers for which the expression is defined as a real number. A piecewise function is defined by different formulas for different parts of the domain. And 4. List the ways to represent a function. List and describe the 4 ways in which a specific function can be described. 1. Written or verbal, that is, description using words. 2. Algebraic, explicit or implicit formulas. 3 is graphically, that's for a visual representation, and 4 numerically, and that often involves using a table of values. Exercise 1. A function f is defined by the formula f of x equals 3x squared minus 2x. A. Express in words how f behaves on the input x to produce the output f of x. Before we write the answer, let's examine function behavior. The mathematical function behaves much like a machine. An x input, processed through the machine 3x squared minus 2x, and an f of x output. Notice, one thing in, one thing out. Now we're ready to express the answer in words. An acceptable answer is, for the input value of x, the function instructs to square the x, then multiply by 3, and then subtract the product of 2 and the input value of x for the output f of x. Let's note, written responses must be presented using proper grammar and correct spelling, college level. This is now a good time to review the correct order of operations. The acronym PEMDAS, P-E-M-D-A-S, might be familiar. As a quick reminder, we read mathematical expressions from the left to the right, and in so doing, we first do the P, or whatever is in parenthesis, first, followed by E, exponents. This also includes roots. And then multiplication or division, whichever appears first. That means if the division appears to the left of multiplication, you do the division first, and then addition or subtraction, as with multiplication and division, whichever appears first, reading from the left to the right. Now, continuing with the function f of x equals 3x squared minus 2x, part B. Evaluate f of 3, f of negative 2, and f of x plus h. Let's begin with f of 3. We write f of 3 equals 3, open parenthesis, squared, minus 2 times open parenthesis, and then we'll fill in the parenthesis with 3. That is, we're substituting the 3 for the x. The rest is arithmetic. Is equal to now 3 times 3 squared is 9 minus 2 times 3 is 6. That would be equal to 3 times 9 is 27 minus 6. So 27 minus 6 is 21. That was fun. Let's do this for negative 2. F of negative 2. This is equal to 3 times open parenthesis squared minus 2 times open parenthesis. Write in negative 2. Every place we had the parenthesis, the rest is arithmetic. This is equal to 3 times negative 2 squared is positive 4, and then negative 2 times negative 2 is positive 4. We continue. 3 times 4 is 12. Add the 4, which gives us 16. Now we're ready to do f of the expression x plus h. To do this, we'd write f of x plus h is equal to 3 times open parenthesis squared minus 2 times open parenthesis, and then in the open parenthesis we will put in the entire expression of x plus h. X plus h again. This is equal to 3 times x plus h squared means x plus h times x plus h. Let's go ahead and distribute the negative 2 to get the expression. Negative 2 times x is negative 2x. Then distributing again would be negative 2h. Multiplying the x plus h times x plus h, we'd have 3 times, then x times x is x squared, plus the middle term would be 2xh, plus h times h is h squared. Let's go ahead and write minus 2x minus 2h. Now we are ready to distribute the 3, which would give us 3 times x squared plus 3 times 2 is 6 times xh plus 3 distributed to the h squared is 3h squared minus 2x minus 2h. So f of x plus h is equal to 3x squared plus 6xh plus 3h squared minus 2x minus 2h. Exercise 2. Given f of x equals x squared minus 5x plus 7, evaluate the following. A. F of x. F of x is the given function, so we'll just write f of x equals x squared minus 5x plus 7. B. F of x plus h. We will put in x plus h every place there is an x in the original function, so this is equal to open parentheses squared minus 5 times the open parenthesis plus 7. Now we'll put in x plus h every place we left the open parenthesis, so one more x plus h. Continuing, x plus h squared means x plus h times x plus h. Then we will distribute the negative 5, so we would have negative 5x distributing again minus 5 times h, and then plus the 7. To multiply the two binomials x plus h and x plus h, we use FOIL, F-O-I-L. First terms together is x squared plus the sum of the product of the inside terms xh plus the outside terms xh is 2xh, then plus the last terms h times h is h squared. Then we can write the minus 5x minus 5h plus 7. Part C. The quantity f of x plus h minus f of x, all divided by h, provided that h does not equal 0. Before we proceed, let's note that this expression is called the difference quotient. Now we can continue. This is equal to, and in the place of f of x plus h, let's put the expression we solved for, which would be x squared plus 2xh plus h squared minus 5x minus 5h plus 7. We'll make sure that's in the parenthesis. Minus, for the f of x, we put in the given expression, which would be open parenthesis x squared minus 5 times x plus 7, close the parenthesis, and all of that divided by h. Let's write this again, distributing the negative to the second expression. So the first stays the same, x squared plus 2xh plus h squared minus 5 times x minus 5h plus 7, and then minus x squared. The negative and negative will make it a positive or plus 5x. Distributing the negative to the 7 would make it a minus 7. All still divided by h. Now some terms cancel. We see that the x squareds cancel. The minus 5x and the plus 5x cancel, and so do the constant 7 and 7. Let's write this again with the canceled terms gone. We have 2xh plus h squared minus 5 times h divided by h. In the numerator, we have a common factor of h in all three of the terms, so let's factor that term out. Factoring out the h, we have h times, then 2x, the h is gone, plus only one h, not h squared anymore, minus 5. We factored out its h, close parentheses, still divided by h. Now, the h's are common, so we can cancel those, the one in the numerator and the one in the denominator. And our final answer simplifies to 2x plus h minus 5. You will need to know the characteristics and the general shape of some common algebraic functions as well as all trigonometric functions. The following is a starting list of a few functions and their domains. Let's start with polynomial. A main characteristic of polynomial functions is that their coefficients are all real numbers and the powers are positive integers. The domain of a polynomial function is all reals. Rational functions are ratios of two polynomials, and the requirement is, given in the domain, that the denominator does not equal 0. Another type of function is an even radical. The most common one would be a square root function. The requirement is that the expression under the square root for the domain must be non-negative. We can express non-negative as x such that g of x is equal to or greater than 0. And if you have an odd radical, that means the power in the nook is an odd number. A common one is the cube root. And for odd roots, the domain is all reals. Exercise 3. Find the domain of the following functions. A. F of x equals 1 divided by the quantity x squared plus x minus 6. First glance, we see that this f of x is a rational function, and we have variables in the denominator. The domain restriction is the denominator cannot equal 0. So we will solve the denominator expression x squared plus x minus 6 not equal to 0. This quadratic factors nicely into a product of two binomials, which they are x plus 3 quantity times x minus 2 quantity, still not equal to 0. Using the zero product property, we set each of the binomials. So we have x plus 3 not equal to 0 and x minus 2 not equal to 0. Simplifying further, we learn that x cannot be negative 3, nor can x be equal to positive 2. We express our answers in interval notation, so this will be expressed as negative infinity to negative 3, union negative 3, comma 2, union 2, comma infinity. B. F of x equals the square root of 25 minus x squared. Observe that square root is even, and so in this instance, the radicand must be non-negative. We will solve 25 minus x squared for equal to or greater than 0. The 25 minus x squared is a perfect square, and it factors to 5 minus x quantity times 5 plus x quantity equal to or greater than 0. There are several ways in which such inequalities can be solved. I will do it one way. First is to find critical values. Those are the values for which something critical happens, such as equals 0. So we have a critical value at x equals 5, setting the term 5 minus x to 0, and x equals negative 5, setting the term 5 plus x to 0. Since we are looking for an interval solution, I will draw a number line and mark the critical values of negative 5, Let's write a 0 above the number line to indicate that at -5, this expression equals 0. Mark +5, which is the other critical value, and also write 0 above that. What we are looking for is the SIGN of the product 5 minus x times 5 plus x. Let's select numbers from each of the 3 regions of the number line to compute the SIGN of the function in that interval. From the leftmost interval, I'll select -6. 5 minus -6 is +11. 5 minus -6, or 5 plus -6, is -1. The product of a positive and a negative is negative. Let's select a number in the middle region. Between a negative and a positive, an ideal number to select is 0. So 5 minus 0, that's a positive. 5 plus 0 is also a positive. The product of 2 positive numbers is positive. And now let's select a number greater than 5. I'll select 6. 5 minus 6 is -1, which is a negative. 5 plus 6 is 11, which is a positive. And the product of a negative and a positive is negative. We need the interval for which the product is equal to or greater than 0. That occurs between -5 and 5. And we get to include the endpoints. So in interval notation, we would use bracket, -5, comma, +5, bracket. C. F of t equals the square root of t plus 1 divided by the quantity t squared minus 1. This function has 2 restrictions to work through to find the domain. The denominator cannot be 0, and the radicand of the square root expression of the numerator must be non-negative. Let's begin with the denominator. The t squared minus 1 cannot equal 0. T squared minus 1 is a perfect square, and it factors to the terms t minus 1 quantity times t plus 1 quantity, still not equal to 0. Using the 0 product property, we can solve for the values, and we get t cannot equal 1 and t cannot equal -1. Let's mark this on a number line. We'll draw a basic number line with holes at -1 and 1. This is to indicate that all numbers except -1 and 1 are acceptable if this is only the denominator. But moving on, now to the radicand of t plus 1. Since it is under a square root, we need to solve t plus 1 to be equal to or greater than 0. We'll subtract 1 from both sides, and this inequality becomes t is equal to or greater than -1. Let's superimpose this restriction onto the current number line. We can solid circle -1 and draw a number line to the right going indefinitely, so t is all numbers -1 or greater. Now, in order to find the domain, we must find the intersection of both the denominator and the numerator terms, and that will occur at not including -1, moving to the right to +1, but not including the +1, and then 1, not including it all the way to +infinity. So in interval notation, it would be -1 to 1, union 1 to infinity. Exercise 4. Evaluate the piecewise defined function at the indicated values. F of x equals x squared plus x for x equal to or less than -1, x for -1 is less than x is less than 1, and 2 for x equal to or greater than 1. So for f of -1, -1 is in the purview of the first piece of the function, x squared plus x, and so in solving this, it would be -1 squared plus -1, which becomes -1 squared is 1 plus -1 is equal to 0. F of 1. That's the third piece where the domain restriction is x is equal to or greater than 1, and that's the constant number 2. F of 0, that's in the second piece of this function. 0 is between -1 and 1, and that piece says f of x equals x, so f of 0 equals 0. And f of 5, again, it is equal to or greater than 1, so it's the third piece, and that would be equal to the constant 2.